Good morning, my YouTube viewers. It is Crystal here. I'm just here because I wanted to do another code review. I was actually not sure that I wanted to do a code review, and the reason why is because I didn't score that well on Kaggle, and because I didn't score that well on Kaggle, I didn't see the point in doing a code review on it, because I really only want to do code reviews on code that scores well. But for reasons I'm not quite sure, Kaggle gave me a bronze medal on it. So I think it's my 41st bronze medal. Let me look on my account. Yeah, it's number 41. And even I had stopped making blog posts and things on all the bronze medals that I had won because I wanted to wait and get a silver medal. And I wanted to start making posts on silver medals. But so far I haven't got a silver medal on anything. And part of the reason for that is because I am a content creator and I don't have time to work on a competition question for the entire 3 weeks to try to improve my score. But that's generally how people who win competitions win, is they work on that particular competition question for the entire time. And then what they'll do is they'll look and see if people have put notebooks up, and then they will look at those notebooks and see if there's anything in those notebooks that can help them improve their score. And so that's basically how it's done. But I really haven't got the time to do that because I create content. And because I create content, I haven't got the time to, work tirelessly on one competition question, because when I do that, I'm not able to create content. But since they gave me a bronze medal, I thought, well, I'll go ahead and do a code review on this. This is Kaggle's Playground Competition, Season 3, Episode 24. And what you have to do is you have to predict the probability that somebody is a smoker based upon a lot of biological statistics and markers in the CSV file. So it is a binary classification problem, but you're predicting on the probability, and because you're predicting on the probability, then you have to use a regression neural network. What I'm going to do is I will leave you a link to the Jupyter Notebook in the description box down below, so you can look at the code if you want at your leisure. I also got a comment on this in addition to a bronze medal. The comment says, "Distinguished, clear NN Jax." So I suspect that even though I didn't score that well, I only scored 71%, and the highest score was about 89%, I believe. I think that because I tried to use a unique algorithm, i.e. using Jax, I think they decided to give me a bronze medal. I'm not sure exactly why they did it. So we're going to go ahead and go through the code review that got me a bronze medal. You can see that I submitted my work to Kaggle and I got a 71 best score. And that's a lot less than the highest score. And I think the reason why they gave me bronze medal was because I used Jax. I used Jax. I will say about Jax is the documentation for Jax is good, but they don't give a lot of sample code. And since Jax API is similar to the NumPy API, then what I do is, if I'm not sure, I'll look on the NumPy documentation, because the NumPy documentation gives example code, whereas the Jax documentation doesn't give a lot of example code. It does give example code, but it doesn't give a lot of example code. So that's just something that I do to get around the fact that Jax doesn't have a lot of sample code. We look at the problem statement. Problem statement is predict on the probability of a smoker status. So basically what you're going to do is you're going to predict on the probability that somebody is a smoker. So I'm assuming that at 0 they're a non-smoker and 1 they're a smoker. And then after we have looked at our problem statement, we're going to import the libraries. So we're going to import Jax. Now Jax is a library that was developed by Google. I believe it's Google Brain. And it's supposed to overtake TensorFlow. Right now they say that Jax is just for research. So if you want to do research, you can use Jax. And that's probably why it doesn't have a lot of documentation. But Jax and TensorFlow are both made by Google, but Jax is scheduled to overtake TensorFlow. So I thought, well, if that's the case, I better start learning Jax. And there's lots of documentation on TensorFlow, but there's not lots of documentation on Jax. And so I thought it'd be a good idea to get in there and produce as much documentation on Jax as I can. And then we're going to import pandas, because that's going to read your data set and convert it into a data frame. We're going to import OS, because what that does is that goes into your operating system and it retrieves files that you're going to need to execute the program. We're going to import sklearn, which provides machine learning functionality. We're going to import matplotlib.pyplot as PLT, which visualizes your data. And we're going to import Seaborn as SNS. And that statistically visualizes your data. So after we have imported our libraries, we're going to retrieve the CSV files by using the OS function to do that. And when we have retrieved our files, we've got a train CSV, test CSV, and sample submission TS CSV. We also set it up to where we can display all of the columns of the data frame. So that's pd.setOption display.maxColumns none, and that displays the maximum columns. And then what we do is we read the 3 CSV files into the program and convert them to data frames. So it's going to be train, test, submission. So you can see train here, it's 24 columns. You can see all 24 columns. And the last column is smoking, and that is your target. So that's going to tell you whether a person is a smoker or not. We look at train info. It's all numeric columns, which is good. That means that we don't have to encode anything. We look at train is in A to check to see if there are any null values. We don't have any null values, so that's good. That means we don't have to impute anything. And then we look at test. And in test has one less column than train. And the reason for that is there's no column that says smoking, because that's what we're going to be predicting on. So we look to see all of the columns are numeric, again, which is good. So we don't have anything to encode. We check for null values. We don't have any null values. So that's good. We don't have anything to impute. And then we look at submission. So this submission is what Kaggle wants to see when we submit our work. And because it's a 0.5, that's telling you that it is a probability. And the thing about, if you were using sklearn logistic regression, then there would be a predict proper, and on the predict proper, that would tell you the probability that somebody was a smoker or a non-smoker. But we're not using sklearn, we're using Jax, and there is no predict proper. I don't know how to make a predict proper function in Jax. I looked it up, so if any of my viewers know how to make a predict proper function, then certainly let me know and I will experiment with that. So we're going to remove the ID column. The reason why we remove the ID column is because all of the rows in Pandas data frame are automatically indexed, so you don't need the column. That's just one extra column you don't need. Now we're going to analyze train. We're going to use seaborn to create a histogram of the target, which is the smoking column. So you can see that you have slightly more, well, you have more non-smokers than you have smokers. We're going to use seaborn to create a heat map of all of the columns, and so you can see the heat maps there, and you can see that some of the columns have a high correlation, but most of them don't. But I didn't go ahead and delete any columns in this that have a high correlation in this instance, because what I found is it doesn't actually improve your score. It actually decreases the score, so I decided to keep all the columns in there. We're going to define our target. Your target is your smoking column, so you're going to pop that out of train, and when you pop it out of train, then what that means is that it's out of train, so it's self-explanatory. Then we're going to standardize data. So when we standardize the data, we're going to take target, train, and test and convert those to Jax arrays, because in order to get an array of data, a matrix or a vector to work, it has to be converted to a Jax array before you can get it to work. And now what we're going to do is we're going to standardize our data, because the thing about a Jax array is the fact that Jax arrays are immutable. And as a result of that, they're more difficult to work with than NumPy arrays, because NumPy arrays are not immutable. So what we have done is we set the standardize the train set, and then we standardize the test set. So you can see that mean tr equals train.mean, std dev tr equals jnp.std train, train equals train minus mean tr over std dev tr. And then we did the same thing with the test set. Mean test equals test.mean, std dev test equals jnp.std test, test equals test minus mean test over std dev test. So you can see that the train data frame is standardized, and you can see that the test data frame is standardized. And it's not a data frame anymore anyway. It's an array, a Jax array. It's two standardized Jax arrays. Now we're going to define the dependent and the independent variables. Y is your target, and it is an dependent variable, and X is an independent variable, and it's train. X test is an independent variable, and it's test. And then we're going to print the shapes, so you can see the shapes of these Y, X, and X test. Now what we're going to do is we're going to use sklearn's train test split function to split the X and the Y variable up into training and testing data sets. and then we're going to print the shapes of all of these so you can see the shapes. So the X test or the X test must be the same format as the X train and the X val, otherwise it won't work. Now we're going to define the regression neural network. So we're going to define the neural network architecture. A neural network architecture has an input node, hidden node, and output node. So the input node is going to be the shape, the number of columns in X train. The hidden size, you can make that as many nodes as you want. I chose 128 in this instance, but you can experiment with other shapes and see what you get. You know, you can experiment with, like, let's say 25 or 25 nodes and see what you get. And then the output size is going to be 1, and that's going to be because it's a regressor. Now what we do is we initialize the weights for the hidden layer and the output layer. So key equals jax.random, PRNG key 42. So the hidden weights equals jax.random.normal, key shape equals input size, hidden bias equals jnp.zeros, hidden bias. So you're just hidden size. So you're just making a matrix of zeros. That's the size of hidden size. Output weights equals jax.random.normal. Key and shape is hidden size, output size. And output bias is jnp.zeros, output size. You're just making a matrix of zeros. That's the size of the output. So now what we're going to do is we're going to train the data into the neural network. We're going to set our learning rate up as to 0.001. We're going to set our number of epochs as to 1,000. And then we're going to set up a for loop that will iterate through the range of the number of epochs. So it will iterate for each example in the training set the number of epochs, which is 5,000 times. So we set up our forward propagation. You want to know what forward propagation is? So this will tell you what forward propagation and back propagation is. We'll ask the question, what is forward propagation and back propagation? Back propagation is the process of moving from right output layer to left input layer. Forward propagation is the way the data moves from left input layer to right output layer in the neural network. And what it does is it strengthens your accuracy, or it reduces the error, really. And then, so we set up our forward propagation. We compute the loss. So your loss is like your mean squared error, really. And then we set up the back propagation. And then we update our weights and our biases. So we update them, and we use the dot product to do that. And basically what a dot product is, the dot product compares two vectors. So the output weights, it's going to compare the dot product of the hidden layer output with the output error. And after we have updated our weights and biases, then we're going to print the loss for every 100 epochs. So we print the loss for 5,000 times. And now what we're going to do is we're going to evaluate the validation set. So your hidden layer input is jnp.dot xval hidden weights plus hidden bias. We're using dot product. That means it is checking it's comparing xval to hidden weights. You've got your hidden layer output. You've got a formula in there that gives you your output. 1 over 1 plus JMP exponent minus hidden layer input. YPred equals JMP dot dot. Hidden layer output, output weights plus output bias. And then you're going to print YPred flatten. So we flattened the YPred. And then now we check the test loss, which is your mean squared error. So test loss equals JMP.mean YPred minus YVal reshape negative 1, 1 to the power of 2. And then we're going to print the test loss, which is 0.2974. Going to calculate the root mean squared error. And we've got a root mean squared error of 0.64. And then what we're going to do is we're going to use Seaborn to create a disk plot of the output. And one thing that I couldn't get right, because the median is off center, and one thing I couldn't get right was I couldn't really get it to go between 0 and 1, which is what it's supposed to do. So what I did was I used Matplotlib to create a diagram, create a chart of the actual values against the predicted values, so you can see that. And now we're going to predict on the test set. So when we predict on the test set, we're going to use the same formula, the same model that we used to predict on the validation set, except we just, instead of xval, we're saying xtest. And so we've got the predictions here. We created a disk plot, a histogram of the predictions using Seaborn, and you can see that the middle is a little bit off center but close to 0, but it's between a -2 and a +2 for the most part. And so what we had to do was because it wasn't giving you between 0 and 1, which is what would have been nice, what we had to do was we had to convert it to a value between 0 and 1, because when you're making predictions on probabilities, the probability is going to be a percentile. So min equals predict.min, max equals predict.max, prediction equals prediction minus min over max minus min. And then we print the prediction, and you can see the prediction. We use Seaborn to make a disk plot, and most of the values are between 0.6 and 0.8, so we don't really even have anything, not much, less than 0.6. So you don't have anything that's between 0 and 0.6. So I wasn't really happy with that, and that's why I wasn't going to make a blog post on this, because I wasn't happy with it. And then what we do is we prepare our submission, and when we prepare our submission, we've got submission smoking equals prediction, submission.toCSV is submission.csv index equals false, submission equals pd.read CSV submission CSV, and then this is your submission. And you can see most of the values are in the 0.7 range. So I wasn't happy with that. I was not happy with that at all, because it didn't give you anything between a 0 and a 0.6 or 0.7. But I went ahead and submitted my work, and when I submitted my work, I got a 71%, which was pretty close to 20 points less than the highest score. And I'm assuming that I got a bronze medal just because I used Jax, but it didn't work out very well. And what I will say is I got a higher score when I used linear regression, because the Jax Regression neural network gives you a regression, and linear regression gives you a value as well. And I scored like a 0.83 or a 0.85, whenever I use the linear regression model. So what I would suggest you do is I would suggest you run the model up, run up a linear regression model, see what score you get, and then run up a regression neural network model and see what score you get, because you may score better just with linear regression, which is what I did. I scored better within linear regression. And so, since I've been talking over 25 minutes on this code review, I better go ahead and conclude this video, because I've covered everything that I want to cover. And what I'd like to say is I'd like to thank all of my subscribers for supporting my channel. If you like my video, please like, subscribe, and share. If you want to be notified whenever I make a new video, then please tick onto the bell button next to the subscribe button. And thank you for watching this code review. I look forward to making more code reviews for you in the future.